1 second is the smallest unit of time you really feel. The space between 2 ticks of a clock, the length of a single breath, far too short for anything important to happen. You could not even finish this sentence in a second. And yet the most decisive second in the history of everything was the universe's very first one. In that single second, 10 billion degrees and falling, the cosmos froze the ratio of its 2 basic building blocks, set loose a flood of ghostly particles still passing through your body tonight, and wrote the recipe for every star that would ever shine. Nothing you have ever done in a second compares. The universe needed only one to decide how much of everything there would be, and it has spent 14 billion years living out that decision. Settle in, subscribe if this is your first time here, because by the end of this, a single second will never feel small again. Now, let's slowly settle into this. Part 1. The explosion that never happened. There is a picture almost everyone carries of how the universe began, and it is wrong in a way that changes everything. In that picture, there is a dark and empty space, vacant and waiting, and then somewhere inside it, a single point detonates. A fireball blooms outward into the surrounding emptiness, throwing matter in all directions the way a bomb throws shrapnel across a field, and that expanding cloud slowly cools and settles into the galaxies and stars we know. It is a clean image, and it is the one most of us were handed as children, and almost every part of it is a misunderstanding. The Big Bang was not an explosion that happened somewhere. There was no surrounding emptiness for it to expand into, no dark room with a spark in the middle, no edge where the fireball met the void. The reason is simple to say and very hard to feel. Space itself was part of what was being created. There was no outside, because the universe was not an object sitting inside a larger nothing. The universe was, and is, everything there is, and at the beginning everything there is was hot, smooth, and pressed together everywhere at once. When we say the universe was smaller, we do not mean it occupied a small corner of a big empty hall. We mean that every distance inside it was shorter, that the whole of it, however large it truly was compressed, with no part of it standing apart from the rest to watch. This is the first thing you have to let go of tonight, and it is worth lingering on because the whole story depends on it. The Big Bang did not happen at a place. It happened everywhere. The spot where you are sitting right now, the air in your room, the chair beneath you, the atoms in your hands, all of it was once part of that uniform fire, and so was every point you can see in the night sky. There is no direction you could point to and say the explosion came from over there. If you could somehow stand in the universe as it was in its first moments, you would find the same blinding conditions in every direction, with no center to walk toward and no boundary to walk away from. The beginning is not behind us in space. It is behind us in time, underneath every place at once. Once you accept that, a stranger and more beautiful question opens up. If the universe began as a smooth, hot everywhere, then we are allowed to ask what that everywhere was actually like at any given moment. We can ask what the universe was made of when it was a year old, or a day old, or an hour old. We can keep pushing backward into conditions hotter and denser than anything that exists now. And we can ask the question this whole video is built around. What was the universe like when it was 1 second old? That number sounds almost like a joke when you first hear it. 1 second. The span of a single breath in, the time it takes to say a short word, the gap between 2 ticks of a clock. We are used to the universe being measured in billions of years, a span so long that the human mind simply rounds it off to forever. To turn around and talk about the universe at the age of 1 second feels like switching from a map of the ocean to a description of a single drop. And yet that 1 second is not a footnote to the story. It is one of the most important seconds that has ever passed, anywhere, for anyone, because almost everything that would ever be made of ordinary matter had its recipe written in that brief window, and the writing was nearly finished before the universe was old enough to be measured in minutes. To get there, we have to walk back through time, and the further back we go, the faster things change. This is one of the quiet surprises of the early universe. Time near the beginning is not evenly paced the way it feels to us. In our daily lives, a second is a second, whether it falls at noon or at midnight, whether you are 5 years old or 50. But in the first moments of the cosmos, the universe was transforming so quickly that a single second contained more genuine change than billions of years would later. The universe at 1 second was profoundly different from the universe at 2 seconds, and almost unrecognizable compared to the universe at 1 minute. The early cosmos lived its most dramatic chapters at a speed we can barely picture, and then slowed and slowed until it reached the long, patient, almost frozen pace of the cosmos we live in now. So when we set our sights on that 1 second mark, we are aiming at a moving target in a place where everything is moving fast. We need a way to pin it down, a way to say with confidence what the temperature was, what the density was, what existed and what did not. We cannot send a probe. We cannot point a telescope at it, because, as we will see, the universe of the first second is hidden behind a wall of light that no telescope can pierce. And yet physicists will tell you, without hesitation, that they know what the universe was like 1 second after the beginning, with more confidence than they know what the inside of the Earth is made of. They will give you a temperature, they will give you a density, they will tell you what particles were present and which had just vanished and which were about to. There is a familiar picture that helps a little here, even though every analogy for the universe eventually breaks. Imagine the surface of a balloon with dots drawn all over it, each dot a galaxy. As you inflate the balloon, every dot moves away from every other dot, and no dot is the center, because the center of the expansion is not on the surface at all. A small creature living on the balloon would see all the other dots receding and might conclude it sat at the middle of the expansion, and so would every other creature on every other dot, and all of them would be right, and none of them would be special. Now, throw away the balloon and keep only the surface, an expanding fabric with no center and no edge, every point moving away from every other, and you have a rough feeling for cosmic expansion. The galaxies are not flying through space away from a central blast. Space itself is stretching and carrying them along everywhere at once. Run that stretching backward and the dots crowd together. The fabric shrinks, the temperature climbs, and you arrive, eventually, at the conditions of the early universe, not at a point in space, but at a moment in time when every distance was small and every place was hot. This is why cosmologists almost never speak of where the Big Bang happened, only of when. The where is everywhere. The beginning is not a location you could visit if you only had a fast enough ship. It is a time you could reach only by travelling backward, and it lies beneath the present moment of every point in the cosmos equally, the shared past of all of space. The fire of the first second was not in one corner of the universe. It was the universe, all of it, in a hotter and younger condition. How can anyone be so sure about a moment no one can see? A moment that lasted less time than it takes to blink. A moment that happened nearly 14 billion years ago. That confidence is not arrogance, and it is not a guess dressed up in mathematics. It rests on the fact that the first second did not vanish without a trace. It left fossils, real and physical, that are still here, still measurable, some of them passing through your body as you listen. To read those fossils, though, we first have to learn how the universe keeps time when it is too young to have a single clock anywhere within it. Because the strangest thing about pinning down that 1 second is that the universe does not measure its own age in seconds at all. It measures it in heat. Part 2. A clock made of heat. The universe does not have a clock hanging on a wall. In the first second of time, there were no atoms to vibrate at a steady rate, no pendulums to swing, no orbits to count, none of the regular motions we use to mark the passing of time. And yet we can still say, with real precision, how old the universe was at any moment in that first second, because the early cosmos carried a different kind of clock inside it, one made not of moving parts, but of temperature. The hotter the universe was, the younger it was. The cooler it grew, the older it became. Heat and age were locked together so tightly that if you tell a physicist the temperature of the early universe, they can tell you its age, and if you tell them the age, they can tell you the temperature. The reason this works comes from the simplest fact about the expanding universe. As space stretches, everything in it spreads out, and a gas that spreads out cools down. You have felt a small version of this yourself. When you let the air rush out of a tire or a spray can, the nozzle goes cold because the gas is expanding and cooling as it escapes. The early universe was doing the same thing on the grandest possible scale, expanding and therefore cooling, steadily and predictably, from the very first instant. Run the film backward, and the universe contracts and heats up. Run it forward, and it swells and cools. The temperature is a direct readout of how far the expansion has gone, which is to say, of how much time has passed. This gives us a beautiful and unusual way to keep time, and it is worth understanding because it is the key that unlocks the whole first second. In the earliest era of the universe, the era we are concerned with tonight, there is a clean relationship between the age of the cosmos and its temperature. To a very good approximation, the time in seconds is set by the temperature, and the rule is almost embarrassingly simple. When the characteristic energy of the particles was around 1 unit that physicists call a million electron volts, the universe was about 1 second old. Push the temperature higher, and the clock reads earlier. Let it fall lower, and the clock reads later. There is a tidy mathematical shape to it, where the age grows as the temperature drops in a steady, predictable curve, but you do not need the equation to feel the point. In the early universe, to know the heat is to know the hour. Let me put some real numbers on this, because they are part of the wonder. When the universe was about 1/100th of a second old, its temperature was around 100 billion degrees. At 1/10th of a second, it had fallen to roughly 30 billion degrees. At 1 second, the number we are chasing, the temperature was about 10 billion degrees. By the time the universe was a full minute old, it had cooled to a few billion degrees, and by 3 minutes to around 1 billion. Each of these moments is a rung on a ladder of cooling, and the rungs come faster the earlier you look. The whole interesting drama, from 1/100th of a second to a few minutes, plays out across a temperature drop from 100 billion degrees down to 1 billion, a fall that sounds enormous and is, and yet it happens in less time than it takes to boil an egg. 10 billion degrees is a number that means nothing until you compare it to something, so let us do that, because comparison is the only way the mind can hold a figure like this. The center of the sun, where hydrogen is being fused into helium right now, sits at around 15 million degrees. That is already hotter than anything you will ever touch, hot enough to power a star for billions of years. The universe at 1 second was not 15 million degrees. It was 10,000 million degrees, very roughly 1,000 times hotter than the core of the sun, and not in one small spot, but everywhere, in every cubic centimeter of all of space at once. There was no cool place to stand. There was no shaded side. The entire universe was a furnace hotter than the inside of any star, filling every location without exception. At that temperature, ordinary matter, as we know it, simply cannot exist, and this is the next idea to settle into. Heat, at bottom, is motion. The hotter something is, the more violently its particles are moving and colliding. We are used to heat that can melt metal or boil water. heat that shakes molecules apart into a gas. But there are higher rungs on that ladder. Push the temperature far enough, and you do not just break molecules into atoms, you break atoms into their pieces, stripping the electrons away from the nuclei to make a glowing plasma. Push further still, and you break the nuclei themselves apart into individual protons and neutrons. At 10 billion degrees, the universe was so hot that complete atoms were impossible, and even most nuclei could not hold together, because any time two particles tried to stick, the surrounding violence would knock them apart almost immediately. The universe at 1 second was too hot to be made of the things we are made of. It helps to dwell on just how lopsided the early timeline was, because it overturns our everyday sense of what an interval means. We think of 1 second as a tiny slice of time, and in our lives it is. But the universe packed more transformation into its first second than it would later pack into millions of years. Between 1 second and 10 seconds, the temperature fell by a large factor, and whole populations of particles vanished. Between 1 second and 1 minute, the universe crossed thresholds that fixed the makeup of all ordinary matter. Compare that to the universe today, where you could sleep through 1,000 years and wake to find the cosmos essentially unchanged, the same galaxies in the same arrangement, the same slow drift. The early universe lived fast and aged quickly. The mature universe lives slow and changes almost imperceptibly. The clock made of heat does not tick evenly. It races at the beginning and crawls toward the end. There is a reason the cooling follows such a clean rule in that earliest era, and it comes down to what the universe was made of. When radiation dominates everything, as it did in the first second, the relationship between time and temperature takes a simple, predictable form, governed only by a few constants of nature and the strength of gravity. It does not depend on the messy details of stars or chemistry or structure, because none of those existed yet. The early universe was, in a strange way, one of the simplest physical systems that has ever existed, a uniform fire whose behavior can be written on a single line, and that simplicity is exactly why physicists can speak about it with such confidence. A complicated thing is hard to predict. A simple thing, even an extreme one, can be pinned down. The universe at 1 second was extreme beyond imagining, and simple beyond almost anything since, and that combination is what lets us read its clock. So the heat is our clock, and the clock tells us the hour, and the hour we are interested in reads 1 second, 10 billion degrees, 1,000 suns in every direction. But a temperature alone is just a setting on a dial. It does not yet tell us what the universe looked like, what filled it, what was happening inside that fire. To answer the question on the screen, the question of what the universe actually looked like 1 second after the beginning, we have to step inside that moment and look around. We have to stand, in our imagination, in a place 1,000 times hotter than the core of a star, denser than anything you have ever encountered, and ask what is there. And what is there will be stranger, emptier of familiar things, and more important to your own existence than almost anything you have ever pictured. So let us go there now, carefully, and see what the universe was at the single second of its life that decided so much of what came after. Part 3. 1 second old. Imagine, for a moment, that you could stand inside the universe when it was 1 second old. Set aside the small problem that you would be destroyed instantly, and that there would be no you, no atoms to build a you from, and simply let your mind be a witness with no body, a point of view floating in the fire. What would you see? The honest answer is that you would see light, and only light, in every direction, with no source and no shadow. There would be no up and no down, because there is no ground and no sky, no object near or far to give you a sense of place. There would be a glare so complete and so even that it would be like being inside the filament of an impossibly bright lamp, except that the lamp is everywhere and you are inside all of it at once. The light would not be coming from somewhere. It would be the substance of the place itself. You would not be floating in empty space dotted with fire. You would be inside a single, seamless medium, a glowing plasma packed so densely that calling it a gas feels wrong. The matter around you would be denser than the core of the sun, denser by far than lead, denser than anything you have ever held, and yet it would not be a solid you could push against, because it is not made of the cold, settled matter we know. It is a churning soup of particles and radiation so hot that everything in it is flying, colliding, transforming, never still. The density at 1 second was something like 500 million kilograms in every cubic meter, which is to say that a single sip of that medium, a thimble's worth, would weigh as much as a small mountain. And this crushing density was not concentrated anywhere. It filled all of space, the same in every direction, with no thinning at any edge, because there was no edge. The strangest feature of all would be the behavior of the light. You might expect that in a place flooded with radiation you could at least see far, that the light would carry your gaze across great distances. The opposite is true. The universe at 1 second was opaque, which means light could not travel freely through it at all. A particle of light, a photon, could move only the tiniest distance before slamming into a charged particle and being knocked in a new direction, then another, then another. The light was trapped, bouncing in a frantic, endless scramble, never getting anywhere. If you tried to look across the room, there would be no across, no view, no distance to peer into. You would be inside a fog made of pure light, a fog so thick that the brightness right at your eye and the brightness a hand's width away would be sealed off from each other, unable to send a clear signal between them. It is the brightest fog imaginable, and you cannot see through it even an inch. There would be no silence in the ordinary sense, but there would be no sound either, no voices, no wind, nothing organized enough to be called a noise. There would only be the relentless churn of particles being created and destroyed. Pairs of matter and antimatter would be flashing into existence out of the raw energy of the radiation, and then annihilating back into light, over and over, everywhere, a constant boil of creation and erasure. The universe, at 1 second, was not a quiet, settled place waiting to become something. It was a frantic, blinding, uniform fire, denser than a star and hotter than a star, with no structure anywhere, no lumps, no clumps, nothing you could point to and name. It was as close to perfectly smooth as anything in the history of the cosmos has ever been. That smoothness deserves a pause, because it is one of the most important things about the moment, and one of the most counterintuitive. We tend to think of the early universe as chaos, as violence, as turbulence, and in one sense it was, with all those particles tearing around at enormous speeds. But on the large scale, the scale of the whole, it was astonishingly calm and even. If you could measure the temperature here, and then over there, and then far away in some other direction, you would find the numbers almost identical, matching to about 1 part in 100,000. The fire was the same everywhere, to a precision that no human-made object can match. There were no galaxies, no clusters, no concentrations of anything, only a vapor of energy spread out with a uniformity so perfect that the tiny imperfections, those 1 in 100,000 ripples, would later become every galaxy and every star. But that is a story for much later. At 1 second, the universe was a smooth and featureless sea of fire, and here is the part that should make the back of your neck prickle. Everything you can see in the night sky tonight, every star, every galaxy, the entire span of the observable universe, 93 billion light-years across, was present in that fire at 1 second. It was not somewhere else, waiting to arrive. It was right there, compressed. The matter that would become the most distant galaxy we can detect, and the matter that would become your own body, were pressed together in the same smooth fire, separated by far less than they are now, all of it part of the same uniform glow. Everything that exists was already accounted for. It was simply too hot, too dense, and too young to have become anything yet. Let the density settle in your mind a moment longer, because numbers this large tend to slide off without leaving a mark. 500 million kilograms in a single cubic meter is not the density of any solid you have ever touched. Lead, which feels impossibly heavy when you lift it, is about 11,000 kilograms in a cubic meter. The universe at 1 second was tens of thousands of times denser than lead, and yet it was not heavy in the way a bar of lead is heavy, because it was not sitting in a gravitational field with a floor beneath it. It was the whole of space, uniformly packed, with nothing to weigh it against. Density, here, is not heaviness, it is crowding. Every tiny region held an enormous number of particles, jammed together far more tightly than the matter in any star, and that crowding is part of why the light could not move, and why even the neutrinos were trapped. The universe was not just hot, it was claustrophobically full, and it would not stay that way, which is the other thing to feel about this moment. The fire was already thinning even as you watched it, because the expansion never paused. With every passing fraction of a second, the medium spread out a little more, the particles drew slightly apart, the temperature dropped another notch. The universe, at 1 second, was not a stable state the cosmos rested in. It was a single frame plucked from a process of relentless, headlong change, a snapshot of something that was already on its way to becoming something else. If you held your witness's view in place for even a few more seconds, you would see the fire dim, the density fall, the violence begin to ease. The 1 second universe was a moment in a fall, the cosmos plunging from the unthinkable conditions of its birth toward the merely extreme, and then the merely hot, and then, across hundreds of thousands of years, toward the calm darkness in which stars could finally form. So this is the universe at 1 second old. It is a fog of light too thick to see through. It is a medium denser than the center of a star, filling every point of space without exception. It is 10 billion degrees, hotter than any furnace, with no cool place anywhere. It is smooth almost beyond belief, with no stars and no galaxies and not even any complete atoms. And it is the common ancestor of everything, the single fire from which the whole later universe, including you, would cool and condense. If you were looking for the most extreme and most important place that has ever existed, you would have a hard time doing better than the universe at the age of 1 second. But a fog of light is not the whole answer, and you may already feel the next question pressing in. What, exactly, was in that soup? Light was the loudest voice, but it was not alone. There were particles in there, particles with names and properties, some of which still exist, and some of which would soon vanish forever. To understand why that 1 second mattered so much, we need to take an inventory of the fire, to count what was present and in what proportion. And when we do, we are going to run straight into one of the most unsettling facts in all of physics, a fact about how very nearly the universe ended up with nothing solid in it at all. Part 4. 1 billion to 1. Let us take an inventory of the fire. If you could sort the contents of the universe at 1 second into bins and count them, you would find a handful of different kinds of particles, and their proportions tell a story that is almost impossible to believe the first time you hear it. The most numerous thing by far was light itself, the photons, packed into every corner of space in staggering numbers. Mixed in with the light were electrons, the same tiny particles that orbit atoms today, but here they were free, racing through the plasma untethered. Alongside the electrons were their antimatter twins, the positrons, identical in almost every way but carrying the opposite electric charge. There were neutrinos, the faint and slippery particles we will come to in a moment, present in numbers nearly as great as the photons. And then there was a trace of something else, a faint contamination of heavier particles, the protons and neutrons, the building blocks of every atomic nucleus that would ever exist. Now, here is the proportion that should stop you. The protons and neutrons, the particles that would go on to make every star, every planet, every rock, every living body, were not the main ingredient of the early universe. They were not even close. They were a rare impurity, a scattering of stray particles lost in an ocean of light. For roughly every one proton or neutron in the early universe, there were more than 1 billion photons. Picture that ratio for a moment. If the photons were grains of sand, you would have to sift through more than 1 billion grains to find a single particle of ordinary matter. The stuff we think of as the real, solid universe, the matter that builds worlds, was a 1 in 1 billion plus trace element floating in a sea of radiation. The universe was overwhelmingly made of light, and matter was the afterthought. That ratio, by the way, is not a vague impression. It is a measured number, one of the most important in all of cosmology, and it has been pinned down with great care from the afterglow of the early universe. There were roughly 1.5 to 2 billion photons for every particle of ordinary matter, and that number has stayed essentially fixed ever since, because as the universe expanded, it diluted the light and the matter together, preserving their ratio. So when we say the early universe was 1 billion to 1 fire, drowning a few specks of matter in a flood of radiation, we are not reaching for a poetic exaggeration. We are reporting a quantity that careful measurement has handed us, a quantity that was already set by the time the universe was 1 second old. But the question that should be forming in your mind is sharper than the ratio itself. Why was there any matter at all? And to answer that, we have to look back to a moment before our 1 second, to the first millionths of a second, when the universe was even hotter and the books had not yet been closed, on a question that determined whether anything solid would ever exist. In that earliest era, matter and antimatter were being created together out of pure energy, in pairs, as they always are, because that is the rule. Energy makes a particle and its antiparticle together, never one alone, and when a particle meets its antiparticle, they annihilate, vanishing back into a flash of light. Creation and destruction, perfectly balanced, a particle and an antiparticle for every act of making, a flash of light for every act of meeting. If that balance had been perfect, the story would have ended there. As the universe cooled and the pairs could no longer be made, every particle would have found its antiparticle, annihilated, and left behind a universe of pure light, glowing and expanding forever, with not a single atom anywhere, no stars, no planets, no one to notice. A universe made entirely of fading radiation. That is not the universe we live in, which means the balance was not perfect. For reasons we still do not fully understand, the early universe contained a tiny, tiny excess of matter over antimatter. For roughly every billion antimatter particles, there were about 1,000,000,001 particles of matter, one extra in 1,000,000,000. When the Great Annihilation came, when each antiparticle found a partner and vanished into light, the billion pairs destroyed each other completely, flooding the universe with photons, and that flood is exactly why there are more than 1 billion photons for every particle of matter today. The light around us is the ash of that annihilation, but the single extra matter particle in every billion had no antiparticle left to meet. It survived. And every proton and neutron in the universe at 1 second, every speck of that rare impurity in the sea of light, was one of those lonely survivors, a leftover from an accounting error that no one has been able to explain. The puzzle of that tiny imbalance has a name, and it is one of the great unfinished problems of physics. Physicists call it baryogenesis, the origin of the matter excess, and decades ago a Russian physicist named Andrei Sakharov laid out the conditions any explanation would have to meet. There would need to be some process that treats matter and antimatter slightly differently, some way for the early universe to fall out of perfect balance, and some moment when the conditions allowed the imbalance to be locked in, rather than smoothed away. Those conditions are clear enough to state. The trouble is that the known forces of nature, when we measure them carefully, do not seem to break the symmetry between matter and antimatter nearly strongly enough to produce the excess we actually see. The asymmetry is too large for the physics we know to explain, which means there must be physics we do not know, some process in the first instance that has so far escaped us. The 1 in a billion tilt is not just unexplained, it is a signpost pointing toward laws of nature we have not yet discovered. It is worth being precise about how the annihilation and the leftover fit together, because the numbers are part of the wonder. Begin with a fire of matter and antimatter in near-perfect balance, 1,000,000,001 matter particles for every billion antimatter particles. As the universe cools and the pairs can no longer be remade, each antimatter particle finds a matter partner and the two vanish into a pair of photons. 1,000,000,000 such annihilations per billion antiparticles flood the universe with light and leave exactly one matter particle behind. So for every surviving particle of matter, you get roughly 1,000,000,000 photons as the receipt of the annihilation that produced it. That is precisely the ratio we measure, more than 1,000,000,000 photons for every particle of matter, and it is no coincidence. The ocean of light that fills the universe and the rare specks of matter floating in it are two halves of the same event, the Great Annihilation, written into the sky as a number we can still read. The light is not separate from the matter, it is the ash, and the matter is the unburned remainder. Sit with that, because it is one of the most personal facts in all of cosmology. Every atom in your body, every atom in the chair you are sitting in the device you are listening on, in the farthest star you have ever seen, is built from that 1 in a billion remainder. You are not made of the main event of the early universe. The main event was the annihilation, the great mutual erasure of matter and antimatter, the flood of light that still fills the sky. You are made of what was left over after the books almost balanced and did not quite. You are the rounding error the universe forgot to cancel. Had the matter and antimatter been exactly equal, exactly symmetric, there would be no you, no Earth, no galaxies, only an endless cold glow. The reason there is something rather than nothing is that, in the first instance, the books did not quite balance, and to this day no one can say for certain why. So our inventory of the fire, at 1 second, comes to this. There was an ocean of light, more than 1,000,000,000 photons for every particle of matter. There were electrons and their antimatter twins, the positrons, still locked in their cycle of creation and annihilation. There were neutrinos in enormous numbers, about to do something remarkable. And there was that precious trace of protons and neutrons, the survivors of the great imbalance, the seed of every solid thing that would ever exist. The universe at 1 second was a fire made almost entirely of radiation, with matter as a faint and improbable contaminant, and that contaminant was us, in our earliest and most scattered form. Among all these ingredients, one was about to change the rules in a way that would leave a fossil still passing through your body tonight. The neutrinos, those faint and slippery particles we have barely mentioned, had spent the entire first second trapped in the fire, along with everything else, jostled and turned by constant collisions. But the universe was cooling, and the conditions that held the neutrinos captive were about to fail. In the next instant of cosmic time, the neutrinos were going to do something that nothing else in the universe could do. They were going to break free, all at once, and begin a journey that has not ended in nearly 14 billion years. To understand why that mattered, and why it still touches you, we have to watch the moment the ghosts went free. Part 5. The night the ghosts went free. To understand what happened next, you first have to meet the neutrino, the most retiring particle in all of physics. A neutrino is a tiny, almost weightless particle that barely interacts with anything at all. It carries no electric charge, so the forces that govern most of the everyday world simply ignore it. It feels only gravity, which is feeble for something so light, and one other force, the weak nuclear force, which acts only across the smallest of distances and only on rare occasions. The practical result is that a neutrino can pass through matter as though the matter were not there. Right now, neutrinos from the sun are streaming through you by the trillions every second, through your body, through the earth itself, in one side and out the other, almost never touching anything. You could line up a wall of solid lead, light years thick, and a typical neutrino would sail straight through it. Neutrinos are the closest thing the universe has to ghosts. But in the first second of the universe, even ghosts could not pass. The reason is density. A neutrino interacts only rarely, yes, but how often it interacts depends on how crowded its surroundings are. In a thin, empty space, a neutrino almost never meets anything, and it flies free. In an unimaginably dense fire, packed with electrons and positrons at 10 billion degrees, even a particle as aloof as the neutrino cannot avoid collisions. There is simply too much in the way. So in the first second, the neutrinos were trapped, not because they suddenly became sociable, but because the universe was so dense that even their rare interactions happened constantly. They were jostled and scattered and turned, locked into the churning fire along with the photons and the electrons, unable to travel any meaningful distance before being knocked off course. The neutrinos were as captive as everything else, prisoners of the crowd. Now watch what the expansion does. As the universe swells and cools through that first second, the fire thins. The electrons and positrons spread out. The collisions grow less frequent, and for the neutrinos, which were only barely held in the first place, a threshold approaches. There comes a moment, right around 1 second of age, at a temperature near 10 billion degrees, when the universe has thinned just enough that the neutrinos stop colliding. Not gradually, but in a cosmic blink. One moment they are jostling against the crowd, turned this way and that. The next moment, the crowd has thinned past the point where it can hold them, and the collisions simply cease. The neutrinos let go. Picture it as best you can, knowing that any picture is a pale shadow of the real thing. Across all of space at once, in every direction, an unthinkable flood of neutrinos that had been trapped and churning for the whole first second suddenly finds the way open. There is no sound to it, no flash, nothing dramatic to the eye, because neutrinos give off no light and announce themselves to nothing. But in that instant, the universe becomes transparent to them. They begin to stream, in straight lines, freely, carrying with them a perfect imprint of the conditions of the universe at the moment they were released. They will fly outward through the expanding cosmos, and they will, for all practical purposes, never be stopped by anything again. The collisions that ruled their whole existence end in a moment, and from that moment forward, the neutrinos are free travelers, gliding through a universe that has agreed at last to let them pass. This event has a name. Physicists call it neutrino decoupling, which is a dry term for one of the most poetic moments in the history of the universe. The neutrinos decoupled, came unstuck, released from the fire that had held them, and the flood of neutrinos set loose at that instant did not disperse or fade. It is still here. It still fills all of space. As the universe expanded over the following billions of years, the neutrinos cooled and stretched, their energy dropping until today. They are extraordinarily cold and faint, but they never went away. They form what we call the cosmic neutrino background, a sea of relic particles left over from the first second, washing through every part of the universe at this very moment. There are, on average, more than 300 of these ancient neutrinos in every cubic centimetre of space, including the space your body occupies right now. What makes this almost unbearably remarkable is the timing. We will talk later about the famous afterglow of the Big Bang, the cosmic microwave background, the relic light that telescopes can detect, and that gives us our clearest picture of the young universe. That light was released when the universe was about 380,000 years old, when it had finally cooled enough to become transparent to photons. That is the oldest light we can see, and it is rightly celebrated as a window onto the infant cosmos. But the neutrinos went free far earlier. They were released at 1 second, not 380,000 years. The cosmic neutrino background is a fossil from a time when the universe was hundreds of thousands of years younger than the oldest light we can detect. It is, quite literally, a fossil older than light, a relic of the first second still drifting through the universe and through you. There is something humbling about this. We often speak of the cosmic microwave background as the edge of what we can know, the oldest thing, the deepest layer the universe will show us. And in terms of light, that is true. But underneath that wall of light, older and quieter, there is this other relic, released when the universe was a single second old, and it has been here the whole time, passing through every star and every world and every body that has ever existed, carrying its silent message from a moment we can never see with any telescope. The first second left a witness. The witness is invisible, nearly massless, and almost impossible to catch, but it is real, and it is everywhere, and it is old beyond the oldest light in the sky. It is worth dwelling on what kind of freedom this was, because it is unlike anything in ordinary experience. When the neutrinos decoupled, they did not merely escape a container. They were released from the entire rest of the universe, set apart from the matter and light they had been mixed with since the beginning, never to rejoin it. From that instant, the neutrinos and the rest of the cosmos went their separate ways, sharing the same space but no longer touching, like two crowds that pass through each other without a single handshake. The neutrinos kept a frozen memory of the universe as it was at 1 second, the temperature, the distribution, the proportions, and they have carried that memory unaltered except by the gentle stretching of expansion ever since. Everything else in the universe went on changing, colliding, building, transforming. The neutrinos simply flew, holding their snapshot of the first second like a photograph that never fades. This same drama, the decoupling of a kind of particle from the rest of the universe, would happen again much later with light, and the comparison is illuminating. Light stayed trapped far longer than the neutrinos, because light interacts with charged particles strongly, and the universe kept free electrons around for hundreds of thousands of years. Only when those electrons finally bound onto nuclei did the light decouple and fly free, producing the relic glow we can see. Neutrinos, being so much more aloof, needed far less thinning before they could escape, and so they decoupled almost at the very start, at 1 second, while the universe was still a furnace. The general rule is the same in both cases. A kind of particle stays locked to the rest of the cosmos until the universe thins enough that its interactions can no longer keep up, and then it breaks away and keeps a permanent imprint of the moment it left. The neutrinos left first, at 1 second. The light left later, at 380,000 years. 2 fossils, 2 release dates, and the earlier one is the one we have never managed to catch. The neutrinos that broke free in that instant have been travelling now for nearly 14 billion years, and they have never stopped. They were flying before the first atom formed, before the first star ignited, before the earth gathered itself out of dust, before the first living thing drew the first breath. And they are not somewhere far away, locked behind a horizon we can never reach. They are right here, in the room with you, passing through your skin and your bones in numbers too large to picture, as they have passed through everything, everywhere, since the universe was 1 second old. To understand what that truly means, we have to turn from the history of these particles to a more intimate fact, the fact that a piece of the first second is moving through your body as you listen. Part 6. They are still passing through you. Right now, as you listen to these words, particles released at the very moment the universe turned 1 second old are passing through your body. This is not a metaphor, and it is not a flourish. It is a plain physical fact, as solid as the floor beneath you. The cosmic neutrino background fills all of space, and your body is a part of space, so it fills your body too. In every cubic centimeter of you, there are, on average, more than 300 of these relic neutrinos at any given instant. And because they are moving, the number streaming through you each second runs into the many billions. They do not stop. They do not interact. They pass through your chest and your eyes and your hands and out the other side and onward into the night, as they have done to everything they have ever met for nearly 14 billion years. Think about how old these particles are compared to anything else you could name. The atoms in your body are old, forged in stars that lived and died long before the sun, and that is a wondrous thing in its own right. But these neutrinos are older. They were already streaming freely when those star-forging atoms were still locked away as raw protons and neutrons in the cooling fire. They are older than the oldest light in the sky, the relic glow that telescopes treat as the boundary of the visible past. They are older than the first star, older than the first atom, older than the first stable nucleus. They date from a time when the universe was a single second old, and they have been moving without rest and without obstacle ever since. When one of them passes through you, you are being touched, however gently, by a piece of the universe as it was 1 second after the beginning of time. There is a quiet strangeness in the fact that we can be so certain these particles are here and yet have such trouble catching even one of them. Their very nature, the aloofness that let them break free at 1 second, is also what makes them nearly impossible to detect now. A neutrino from the Sun, which is far more energetic than these relics, is already maddeningly hard to capture. To catch solar neutrinos, physicists build detectors the size of buildings, filled with thousands of tons of fluid, buried far underground to shield them from everything else. And even then, they record only a handful of events a day out of the trillions passing through. The relic neutrinos from the first second are far colder, far gentler, far harder to register. No experiment has ever directly detected one. They are the most abundant matter particles in the universe, more numerous than all the particles in all the stars, and we have never caught a single one of them in the act. And yet we know they are there, with confidence, because they leave fingerprints we can read in other ways. The amount of helium the universe made in its first minutes depended on exactly how fast the early cosmos was expanding, and that expansion rate depended on how many kinds of particles were present, including the neutrinos. When physicists measure the helium and compare it to their calculations, the numbers only fit if the neutrinos were present in just the right amount. The relic neutrinos also left a faint imprint on the afterglow of the Big Bang, a subtle effect on the patterns in that ancient light, and that imprint too has been measured, and it agrees. So even though we have never held one, we know the cosmic neutrino background is real because the universe does not make sense without it. The first second signed its name in a way we can still read, and the signature checks out. There are physicists working right now on the dream of catching these relics directly, of building an instrument sensitive enough to register a particle so faint and so cold that it has slipped past every detector ever made. The proposed experiments are extraordinarily difficult, pushing at the very limits of what measurement can do, and success is far from guaranteed. But imagine what it would mean. To catch a relic neutrino would be to hold, for an instant, a particle that has been flying since the universe was 1 second old, to read directly the conditions of that single second, to touch the fire at the moment the ghosts went free. It would be the closest thing to time travel that physics could ever offer, not a journey back, but a fragment of the past arriving, intact, in the present, the way the light of a distant star is the past arriving in your eye. This is the thing about the first second that is hard to shake once you have understood it. We tend to imagine the beginning of the universe as something safely far away, sealed off, finished, a chapter closed billions of years ago in a place we can never reach. But the first second did not close. It left witnesses, and the witnesses are not in a museum or a textbook or a distant corner of the sky. They are inside you. The relic neutrinos passing through your body as you breathe are a direct, physical, unbroken connection to the universe at the age of 1 second. The beginning is not only behind us. In the gentlest possible way, it is still moving through us, every second of every day, and it always has been. The indirect evidence is worth understanding a little more closely because it shows how physicists can be certain of something they have never seen. The expansion rate of the early universe depended on how much energy was packed into it, and that energy was shared among all the kinds of particle present, including every flavor of neutrino. If there had been more kinds of neutrino, the universe would have expanded faster, the neutron-proton ratio would have frozen at a different value, and the universe would have made a different amount of helium. So the measured helium acts as a kind of particle counter, telling us how many neutrino species were present in the first second, and the answer it gives is 3, exactly the 3 kinds we know from experiments on Earth. The afterglow of the Big Bang carries the same count, encoded in the fine details of its patterns, and it agrees. 2 completely independent measurements, the helium and the relic light, both insist that 3 flavors of neutrino were streaming through the first second, which is a remarkable thing to be able to say about particles we have never directly caught. There is also a quiet motivation behind the effort to catch one at last. A relic neutrino carries information from earlier than any photon we can detect, from 1 second instead of 380,000 years. And so the cosmic neutrino background is, in principle, a window onto a layer of the past that light can never show us. If we could read it directly, we could check our picture of the first second against the thing itself, rather than against its consequences. The experiments proposed to do this are at the very edge of what is possible, relying on capturing a relic neutrino as it is absorbed by a carefully prepared atomic nucleus, a signal so faint that distinguishing it from background noise is a monumental challenge. No one has done it. It may take a generation more, but the prize is a direct touch of the universe at 1 second, and that is the kind of prize that keeps people building impossible machines. There is a comfort in this that is easy to miss beneath the strangeness. We spend so much of our lives feeling small against the scale of the cosmos, separated from its grandeur by unbridgeable distance and time. And yet a piece of the universe's very first second is not far away at all. It is here, with you, constantly, gently, a quiet flood that has never once paused since the beginning. You do not have to travel to the early universe or build a telescope to reach it. It comes to you, through you, every second, as it always has. The beginning keeps you company, whether you notice it or not. So the first of the great events at 1 second, the freeing of the neutrinos, left a fossil that is still here, still passing through you, older than light. But it was not the only thing happening in that crowded second. While the neutrinos were breaking free, another process was unfolding in the fire, slower and quieter, a kind of contest between 2 particles that would decide the chemical makeup of the entire universe. It was a tug-of-war between the proton and the neutron, and right around that 1 second mark, the contest was about to be frozen in place, its outcome locked in for the rest of cosmic history. To see why a single ratio, settled in that 1 second, would reach into every star that has ever shone, we need to watch the moment the coin froze in the air. Part 7. The coin that froze in the air. To follow this next event, you need to know one small fact about the two particles at the center of it. Protons and neutrons are the two kinds of building block that make up atomic nuclei, and they are very nearly identical twins. They have almost the same mass, they feel the same powerful nuclear force, and in the fire of the early universe, they could turn into each other freely. A proton could become a neutron, and a neutron could become a proton through the same weak nuclear force that governs the neutrinos. In the heat of the first second, these conversions were happening constantly, in both directions, so that at any instant, the population of protons and neutrons was being shuffled back and forth, a particle changing its identity, then changing back, an endless trading of roles. But the twins are not perfectly identical, and one tiny difference between them turns out to matter enormously. The neutron is very slightly heavier than the proton by a little over 1 part in 1,000. That sounds trivial, and in everyday terms it is, but in the language of energy, it means that it costs a little more to make a neutron than to make a proton. And nature, given a choice and enough jostling, tends to favor the cheaper option, the lower energy one. So even while the conversions ran in both directions, the balance was tilted. At any given temperature, there were always somewhat more protons than neutrons, because protons were slightly easier to make. When the universe was very hot, the tilt was gentle, because the heat was so overwhelming that the small mass difference barely registered, and protons and neutrons were nearly equal in number. But as the universe cooled, the tilt grew steeper, and neutrons became increasingly outnumbered. Here is where the clock comes back into the story, because two processes were now racing against each other. On one side was the weak force, busily converting protons and neutrons back and forth, trying to keep their populations in step with the falling temperature. On the other side was the expansion of the universe, relentlessly thinning the fire and cooling it. The conversions depended on particles meeting and interacting, and as the universe spread out, those meetings grew rarer. There came a point, right around that 1 second mark, when the universe had thinned and cooled so much that the weak force could no longer keep up. The conversions slowed, faltered, and effectively stopped. The proton and neutron populations could no longer adjust. Whatever ratio they happened to have at that moment was now locked, frozen in place, because the process that had been keeping it flexible had failed. Picture it as a coin spinning in the air, a coin that has been flipping between two faces, proton and neutron, fast enough that the ratio of one to the other was always settling smoothly toward the value the temperature demanded. As the universe cools, the coin spins slower and slower, the trades less and less frequent, until at last, around 1 second, the spinning stops and the coin is caught midair, held, fixed at whatever count it had reached. And the count it had reached was about 1 neutron for every 5 protons. That was the ratio frozen into the universe at the moment the weak force gave out. 1 neutron for every 5 protons, set not by chance in any one place, but the same everywhere, across all of space at once, like a single coin that somehow landed the same way in every corner of the cosmos. The freezing was not perfectly sharp, and the story has one more turn, because the neutron has a secret. A free neutron, one not bound inside a nucleus, is unstable. Left to itself, it falls apart, decaying into a proton and a few other particles, with a half-life of about 10 minutes. So, even after the ratio froze at 1 neutron to 5 protons, the clock kept ticking, and during the next few minutes, some of those lonely neutrons quietly decayed into protons. By the time the universe was ready to start building nuclei, a few minutes later, the ratio had drifted further, from about 1 neutron in 5 to roughly 1 neutron in 7. The neutrons were slipping away, decaying one by one, and the only thing that could save the survivors was to lock them inside nuclei before they fell apart. But that rescue belongs to the next chapter. For now, the essential fact is that the universe, at around 1 second, had set the proportion of its two basic building blocks, and that proportion was now fixed. There is a subtlety worth drawing out about why the ratio froze when it did, because it captures something general about the early universe. Two clocks were running side by side. One was the clock of the weak interactions, measuring how often a proton or neutron got converted, a rate that fell as the universe thinned and the particles spread apart. The other was the clock of the expansion itself, measuring how fast the universe was stretching and cooling. As long as the conversions ran faster than the expansion, the ratio could keep adjusting, tracking the temperature smoothly. But the conversion rate fell more steeply than the expansion rate, and at some point the two clocks crossed. Past that crossing, the expansion was winning, the conversions could no longer keep pace, and the ratio was effectively frozen. This crossing of two rates, the reaction rate falling below the expansion rate, is the same mechanism that froze the neutrinos free a moment earlier, and it is one of the most important ideas in all of early universe physics. Again and again, the cosmos holds something in balance until the expansion outruns the process that maintained it, and then that thing is locked in for good. The exact value at which the ratio froze, about 1 neutron for every 5 protons, came directly from the temperature at the moment of freezing and the small mass difference between the two particles. At the freeze-out temperature, the energy available was a little less than the mass gap between neutron and proton, so neutrons were already somewhat disfavored, and that disfavoring set the 1 to 5 figure. Had the weak force been a little stronger, the conversions would have kept pace to a lower temperature, the ratio would have frozen later and lower, and fewer neutrons would have survived. Had the universe expanded faster, the freeze would have come earlier and higher, and more neutrons would have been trapped. The number 1 to 5 is not a round figure or a coincidence. It is the precise output of a race between two rates decided by the constants of nature, and it is the seed from which the helium of the universe would grow. Everything downstream, the recipe of the stars, the chemistry of the cosmos, hung on where those two clocks happened to cross. It is worth pausing to feel how delicate this all was. The whole outcome hung on that tiny mass difference between the proton and the neutron, a little more than 1 part in 1,000. If the neutron had been a little lighter, closer to the proton, more neutrons would have survived the freeze, and the universe would have made far more heavy elements early on. If the neutron had been much heavier, almost none would have survived, and the universe would have been left as nearly pure hydrogen, with no helium to speak of. The exact tilt of that contest, decided by a sliver of mass and the precise moment the weak force gave out, set the recipe. And the timing of that moment, the moment the coin froze, was the 1 second mark we have been circling all along. The ratio was not set at the beginning of time, and it was not set at the formation of the first star. It was set in that 1 cooling second, by a race between two of the most fundamental processes in nature. So the second great event of the first second was this freezing of the neutron to proton ratio, 1 neutron for every 5 protons, drifting toward 1 in 7, locked in by the failure of the weak force to keep pace with the expanding fire. On its own, a ratio of particles might sound like a piece of bookkeeping, a technical detail of interest only to physicists. But it is far more than that. That single frozen ratio would determine how much helium the universe could ever make, and the amount of helium in the universe is not a small thing. It is written into the composition of every star, including the Sun, and it shaped the entire chemical history of the cosmos. To see why a number settled in 1 second still governs the makeup of every star in the sky, we have to follow that frozen ratio forward and watch it become the universe's first and most enduring recipe. Part 8. The recipe written in a heartbeat. Let us follow that frozen ratio forward and see what it builds. The neutrons that survived the freeze were doomed if they stayed alone, because a lone neutron decays in about 10 minutes. Their only escape was to join with protons and lock themselves inside stable nuclei, where the binding would protect them from falling apart. And that is exactly what happened a few minutes after our 1 second, when the universe had cooled enough for nuclei to form. Almost every surviving neutron found a proton and bound to it, and then those pairs gathered into the nucleus of helium, which holds 2 protons and 2 neutrons together in a tight, stable package. The neutrons were saved by being built into helium, and the amount of helium the universe could make was set almost entirely by how many neutrons had survived to that point. And how many neutrons survived was set by the ratio that froze at 1 second. The arithmetic is simple enough to follow, and it is one of the most satisfying calculations in all of science. By the time nuclei began to form, the ratio stood at roughly 1 neutron for every 7 protons. Take a sample of that mixture, say 2 neutrons and 14 protons, to keep the numbers easy. The 2 neutrons each pair with a proton, and those pairs assemble into a single helium nucleus, using up 2 neutrons and 2 protons. That leaves 12 protons unattached, and a bare proton is simply the nucleus of hydrogen, so you end up with 1 helium nucleus and 12 hydrogen nuclei. Now weigh them. The helium nucleus is about 4 times as heavy as a single hydrogen nucleus, so that 1 helium represents about 4 units of mass, while the 12 hydrogens represent 12 units. 4 out of 16 total is 1/4. About 1/4 of the ordinary matter ends up as helium, and about 3/4 remains as hydrogen. That is the recipe. Roughly 75% hydrogen, roughly 25% helium, by mass, with only the faintest traces of anything else. And here is the line that should land with full weight. That ratio, 3/4 hydrogen to 1/4 helium, is exactly what we measure across the universe today. When astronomers examine the oldest stars, the most pristine gas clouds, the material that has been least altered since the beginning, they find very close to 25% helium again and again, in every direction, near and far. The recipe written in the first second is the recipe we still read in the sky. The sun is about 1/4 helium. The gas between the galaxies is about 1/4 helium. The universe kept the proportions it was given when it was 1 second old and a few minutes past, and it has carried them, almost unchanged, for nearly 14 billion years. Take a moment to appreciate how strange and beautiful that is. The amount of helium in the sun was not decided by the sun. It was decided before the sun existed, before the Earth existed, before any star had ever formed, in a contest between protons and neutrons that froze when the universe was 1 second old. Every star you can see in the night sky began its life with that same 1/4 helium composition, inherited from the first minutes of the cosmos. Stars make their own additional helium as they burn, and they forge heavier elements in their cores, but the original helium they were born with, the baseline that every star started from, was made in the first 3 minutes and set by the first second. When you look up at a star, you are looking at a body that carries, in its very substance, a number that was settled in the universe's first heartbeat. This is why physicists care so much about the first second, and why they have worked so hard to understand it. The helium fraction of the universe is one of the great success stories of cosmology, a prediction made from the physics of the first minutes that matches the observed universe with stunning accuracy. The men who first worked this out, decades ago, realized that if the universe really began hot and dense, it should have cooked up a specific amount of helium, and they calculated what it should be. And then, years later, when the measurements came in, the universe agreed. The recipe written in a heartbeat was confirmed by the recipe found in the stars. It is one of the strongest pieces of evidence we have that the hot beginning really happened the way we think it did, because the fingerprints match. And it could so easily have been otherwise. The recipe was not inevitable. It depended on the exact strength of the weak force, on the precise mass difference between the proton and the neutron, on how fast the universe expanded, on the lifetime of the free neutron. Change any of these, even modestly, and the recipe changes. A universe that froze its ratio at a different value would have been born with too much helium and too little hydrogen, or almost no helium at all. The chemistry of such a universe would have been different from the start, the lives of its stars different, the raw material for planets and worlds different. The fact that our universe was given a balanced recipe, plenty of hydrogen to fuel long-lived stars and build water, a healthy measure of helium, only the faintest trace of anything heavier, is not something the early universe had to do. It is simply what our universe did, in its first second, for reasons woven into the fundamental constants of nature. The story of how we came to know this is one of the finest in 20th century science, and it deserves a moment. In the 1940s, a physicist named George Gamow and his younger colleagues, among them Ralph Alpher and Robert Herman, took seriously the idea that the universe had begun hot and dense, and they asked what such a beginning should have cooked up. They reasoned that, in the first minutes, the universe would have fused its protons and neutrons into light elements, and they set about calculating how much. Their early work was rough, and some of their specific ideas turned out to be wrong, but the core insight was right and revolutionary. A hot beginning should leave a definite, calculable fingerprint in the abundance of the lightest elements, and it should leave behind a bath of relic radiation, cooled by expansion, still filling the sky. They even estimated, remarkably, what the temperature of that relic radiation should be, a few degrees above absolute zero, decades before anyone found it. For a time, these ideas sat largely ignored, because no one had a way to test them, and because a rival picture of a universe with no beginning at all held wide appeal. But the prediction was patient. When the relic radiation was finally discovered, by accident, in the 1960s, and measured to be just a few degrees above absolute zero, almost exactly as the early calculations had suggested, the hot beginning went from speculation to established science. And as the measurements of the light elements grew more precise over the following decades, the helium and the deuterium and the lithium all falling close to what the theory of the first minutes demanded, the case became overwhelming. The recipe Gamow and his colleagues had glimpsed in the 1940s was confirmed, element by element, by the universe itself. It stands today as one of the great triumphs of physics, a calculation about the first 3 minutes of time that the whole sky has since been found to obey. So the frozen ratio became the recipe, and the recipe became the composition of every star, and all of it was set in the universe's first, second, and the few minutes that followed. But we have skipped over something in our hurry to reach the helium. Between the freezing of the ratio at 1 second and the building of nuclei a few minutes later, the universe passed through one more transformation, a sudden purging of particles that flooded the cosmos with a final surge of light and left a permanent mark on the relics we can still measure. Just past 1 second, the electrons and their antimatter twins reached the end of their long dance, and what happened next would forever separate the temperature of the light from the temperature of the neutrinos that had just gone free. To understand the universe that emerged from the first second, we have to watch the first great burning. Part 9. The First Great Burning. Just past the 1 second mark, the universe staged a purge. To understand it, recall the electrons and positrons we counted in our inventory of the fire, present in enormous and nearly equal numbers, matter and antimatter, twins locked in a constant cycle of creation and destruction. For the whole first second, that cycle was balanced. The fire was hot enough that whenever an electron met a positron and annihilated into light, the radiation was energetic enough to make a fresh electron-positron pair somewhere else, replacing what was lost. Creation and destruction ran in step, and the population of electrons and positrons held steady, a churning equilibrium maintained by the heat. But the universe was cooling, and equilibrium has a breaking point. The making of an electron-positron pair costs a certain minimum amount of energy, because these particles have mass, and mass costs energy to create. As long as the radiation carried more than that threshold, pairs could be remade as fast as they annihilated. But as the temperature fell past the point where the typical photon could no longer afford to make a pair, the replacement stopped. Annihilation continued, because electrons and positrons kept meeting and destroying each other, but now nothing was being made to take their place. The cycle, once balanced, tipped into one-way collapse. Across all of space, the enormous populations of electrons and positrons began to annihilate without replacement, pouring themselves into light, and they did not stop until almost all of them were gone. This was the first great burning, a near-total annihilation of the universe's electrons and positrons into radiation, happening everywhere at once, in the seconds and minutes after our 1 second. And it was not a quiet fade. All the energy that had been bound up in those countless particles was dumped into the photons, the light, in a final surge. The radiation, already the dominant presence in the universe, was suddenly fed a fresh meal of energy from the dying matter and antimatter. The light grew hotter, or more precisely, it cooled more slowly than it otherwise would have, buoyed up by the energy of the annihilating pairs. The photon bath was reheated, given a boost that the rest of the universe did not share. And here is the detail that makes this more than a footnote, the detail that ties the burning back to the neutrinos. Remember that the neutrinos had already gone free just before this happened, at the 1 second mark. They had decoupled, broken away from the fire, and were now streaming along on their own, no longer in contact with the rest of the universe. So when the electrons and positrons annihilated and poured their energy into the photons, the neutrinos got nothing. They had already left the room before the final surge of warmth arrived. The photons were reheated, the neutrinos were not. And from that moment on, the light and the neutrinos carried slightly different temperatures. The light a little warmer, the neutrinos a little cooler, because the light had received a parting gift of energy that the neutrinos, having departed a moment too early, never shared. That difference is still measurable today, and it is one of the quiet triumphs of cosmology. The relic light of the early universe, the cosmic microwave background, sits today at about 2.7 degrees above absolute zero. The relic neutrinos, the cosmic neutrino background, sit at a slightly lower temperature, just under 2 degrees above absolute zero. The exact ratio between those two temperatures was set by the energy the annihilation poured into the light after the neutrinos had gone, and the predicted ratio matches the physics precisely. So the slightly cooler temperature of the neutrino background is a direct fingerprint of the first great burning, a record that the neutrinos left before the electrons and positrons made their final exit into light. Two relics, released moments apart, carry two slightly different temperatures, and the gap between them is a measure of exactly what happened in those seconds after the universe turned one. There is a tidy lesson hidden in all this about how the early universe worked. Each major event left the relics around it marked, and by comparing those relics, we can reconstruct the sequence of what happened and when. The neutrinos went free, then the electrons and positrons burned away into light, and the order of those two events is written permanently into the temperatures of the two backgrounds. We did not witness the burning. No one was there to see the electrons and positrons annihilate across the sky. But the event signed its name in the difference between two numbers, the temperature of the light and the temperature of the neutrinos, and we can read that signature today, nearly 14 billion years later, in the faint cold relics that fill all of space. It is worth slowing down on why this reheating happened only to the light and not to the neutrinos, because the logic is precise and the consequence is permanent. Think of the universe just after 1 second as holding two reservoirs that have stopped exchanging energy. One reservoir is the neutrinos, which decoupled at 1 second and are now coasting on their own. The other is everything still in contact, the photons together with the electrons and positrons. When the electrons and positrons annihilate, their energy has nowhere to go but into the photons, because the photons are the only thing they are still talking to. The neutrinos, having already left, receive none of it. So the photon reservoir is topped up, while the neutrino reservoir is not. And from that point forward, the photons are warmer than the neutrinos by a fixed calculable factor. The number works out to the photons being warmer by a ratio that comes straight from counting how many kinds of particle dumped their energy into the light, and that predicted ratio is one of the cleaner results in the subject. This is the kind of detail that separates a story we tell from a science we test. Anyone can say the early universe was hot and full of particles, but to predict that the relic neutrinos should today be measurably cooler than the relic light by a specific factor, and to derive that factor from the timing of two events in the first seconds, is a precise and falsifiable claim. The relic light has been measured to extraordinary accuracy, sitting at about 2.7 degrees above absolute zero. The relic neutrinos, harder to pin down, are inferred to sit just under 2 degrees, exactly where the annihilation physics says they should. The gap between those two cold numbers is a fossil of the order of events in the first seconds, the neutrinos leaving, then the electrons and positrons burning away. Few things capture the strange reliability of early universe physics better than the fact that we can predict and confirm the temperature difference between two seas of relic particles released moments apart 14 billion years ago. There is a small irony worth noticing in this purge, given how the story began. The universe started, in its first instance, with matter and antimatter in near-perfect balance, and most of that balance had already been spent in the great annihilation of the first microseconds, the one that left the 1 in a billion excess of matter. The burning of the electrons and positrons just after 1 second was a smaller, later replay of that same process, the last large population of antimatter in the universe finally meeting its end. After it was over, antimatter all but vanished from the cosmos for good. The universe would not see antimatter in any quantity again, except in rare, fleeting bursts near violent objects like exploding stars and the surroundings of black holes. The first, second, and its immediate aftermath were the closing scenes of antimatter's brief reign. From then on, the universe belonged almost entirely to matter and to light. By the time the first great burning was finished, the universe had changed in a fundamental way. The constant boil of electron-positron creation and annihilation, which had churned through the entire first second, was over. The antimatter that had filled the early cosmos was now almost entirely gone, annihilated into light, leaving behind only the rare electrons that matched the rare surviving protons, the leftovers of that 1 in a billion imbalance from the very beginning. The universe was settling, in its violent way, toward a simpler state, a sea of light, a thin haze of surviving matter, and the streaming neutrinos gliding through it all. The frantic, blinding, ever-churning fire of the first second was beginning, at last, to calm. Yet even as the universe quieted, it was not finished making things. The most important act of creation was still to come, in the minutes just ahead, when the universe would assemble the first nuclei and forge the elements that fill it to this day. To witness that, we have to watch a bottleneck break. Part 10. The bottleneck breaks. The universe wanted to make nuclei, and for several minutes it could not. This is one of the most surprising twists in the whole story, because you might think that once you have protons and neutrons in a hot, dense fire, building nuclei would be the easy part. The protons and neutrons were certainly trying. To build helium, the universe first has to take the simplest step, joining a single proton to a single neutron to make a heavier form of hydrogen called deuterium, a proton and a neutron bound together. Deuterium is the first rung on the ladder, the necessary stepping stone, because you cannot leap straight to helium. You have to build up through deuterium first. And the protons and neutrons in the early universe were colliding constantly, forming deuterium all the time. The trouble was that the deuterium could not survive. The problem was the light itself. Deuterium is a fragile thing, a proton and a neutron held together by a relatively gentle grip, easily broken apart by a sharp enough blow. And the early universe was flooded with photons, more than 1 billion of them for every particle of matter, many of them energetic enough to shatter a deuterium nucleus the instant it formed. A proton and a neutron would find each other and bind into deuterium, and almost immediately a passing photon would smash them apart again. The universe was caught in a frustrating loop, building the first rung of the ladder over and over, and having it kicked away each time before anything heavier could be assembled. This logjam has a name. Physicists call it the deuterium bottleneck, and it held the universe back from making elements for the first few minutes of its life, not because the protons and neutrons were unwilling, but because the light kept tearing their first efforts apart. What breaks the bottleneck, in the end, is patience, the slow cooling of the expanding universe. As the cosmos continued to swell and the temperature kept falling, the photons grew gentler. There came a point, around 3 minutes after the beginning, when the universe had cooled to roughly 1 billion degrees, and the typical photon no longer carried enough punch to break deuterium apart. Suddenly, the first rung of the ladder could hold. A proton and a neutron would bind into deuterium, and this time the deuterium would survive, lasting long enough to be joined by other particles to climb the ladder toward helium. The bottleneck broke, and when it broke fast. Picture the scene across the whole sky at once. For minutes, every attempt at building has failed, the deuterium forming and shattering, the universe straining against a barrier it cannot pass. Then the temperature slips below the critical threshold, and all at once, everywhere, the deuterium begins to hold. And once that first rung is secure, the rest of the climb happens in a rush. Deuterium captures another proton or another neutron, builds toward helium, and within a few hundred seconds, the surviving neutrons are swept up almost completely, bound into helium nuclei across all of space simultaneously. The universe, held back for minutes, suddenly forges its first permanent matter in a brief, furious burst of creation, the same process unfolding in perfect step in every region, because every region had been waiting at the same bottleneck for the same cooling to arrive. This burst of building is what physicists call Big Bang nucleosynthesis, the making of the first nuclei in the first minutes of the universe, and it was over almost as soon as it began. The window was narrow. The universe had to be cool enough for deuterium to survive, but still hot and dense enough for nuclei to keep fusing, and that window lasted only a matter of minutes. By the time the universe was perhaps 20 minutes old, the fire had thinned and cooled too far for any more building to happen, and the cosmic kitchen closed. In that brief span, the universe made its hydrogen and its helium in the proportions we have already discussed, 3/4 to 1/4, and it made small traces of a few other light things, a little of a lighter form of helium, a trace of deuterium that escaped being built all the way up, and the faintest whisper of lithium, the third element. And then it stopped, because the conditions for fusion were gone. What it did not make is just as telling as what it did. The early universe made no carbon, no oxygen, no iron, no gold, none of the heavier elements that fill the world around you and build your own body. The reason is a quirk of nuclear physics, a gap in the ladder. There is no stable nucleus with 5 particles, and none with 8, and these gaps act like missing rungs that the rapid, brief process of the first minutes could not leap across. To build carbon and the heavier elements, the universe would have to wait hundreds of millions of years until stars formed and their cores, burning slowly over enormous stretches of time, found a way across those gaps. So the first minutes gave the universe only the lightest elements, hydrogen, helium, and a trace of lithium, and left everything heavier for the stars to make later. The deuterium in every drop of seawater, the helium in every star, dates from those first minutes. The carbon in your cells and the iron in your blood had to wait for stars to die. The narrowness of the window deserves a moment of wonder, because it is part of why the universe turned out the way it did. The cosmic kitchen was open for only a few minutes, bounded on one side by the deuterium bottleneck, which kept it shut until about 3 minutes, and on the other by the relentless cooling and thinning, which shut it again by perhaps 20 minutes. In that brief opening, the universe had just enough time to build hydrogen and helium and stop. If the bottleneck had broken earlier, or if the universe had stayed hot and dense a while longer, more building could have happened, and the cosmos might have emerged with a different mix, perhaps heavier on helium, perhaps with more of the heavier light elements. Instead, the timing left the universe overwhelmingly as hydrogen, the simplest element, a single proton, with helium as the only major companion. And hydrogen, as it happens, is the fuel that lets stars burn for billions of years and the element that joins with oxygen to make water. A universe that burned through its hydrogen in the first minutes would have been a very different and probably far more barren place. The short opening of the cosmic kitchen left plenty of the simplest fuel intact. It is also worth lingering on the strangeness of a furnace with no walls. Every furnace you have ever encountered has a boundary, a container that holds the heat, a place where the fire is and a place where it is not. The furnace of the first minutes had no walls and no outside. It was not a fire burning in a hearth. It was a fire that was everywhere, forging nuclei at every point of space at once, the same reactions running in perfect synchrony across the entire universe. There was no center where the cooking was hotter and no rim where it petered out. When we say the universe made its helium, we mean that every region of the cosmos, separated by distances that would later become billions of light years, was carrying out the identical nuclear assembly at the identical moment because every region had started from the same conditions and cooled at the same rate. It is the only time in all of history that the entire universe acted as a single, unbounded furnace, and it lasted only minutes. So the third great consequence of the first second, following on from the freezing of the ratio, was this making of the light elements, the only time in cosmic history when the entire universe acted as a single furnace, forging matter everywhere at once. The recipe set at 1 second was now baked into real nuclei, hydrogen and helium spread uniformly across all of space, the raw material from which every galaxy and every star and eventually every world would be built. The first second decided the proportions, and the first minutes turned those proportions into substance. But all of this raises a question we have been postponing, a question that should be nagging at you by now. We cannot see the first second. No telescope can pierce that wall of light. So how, exactly, do we know that any of this is true? Part 11. How we read a second we cannot see. We cannot see the first second, and it is worth being honest about exactly why. The universe stayed opaque to light for a long time, hundreds of thousands of years, because as long as it was hot enough to keep electrons free, those electrons scattered the photons endlessly, and no clear image could form. Only when the universe was about 380,000 years old did it cool enough for electrons to settle onto nuclei, the fog finally lift, and light travel freely. That released light is the cosmic microwave background, the oldest light we can detect, and it forms a wall beyond which no telescope can ever look. Everything earlier, including our 1 second, is hidden behind that wall of light. No instrument will ever take a picture of the universe at 1 second of age, because there is no light from that era that can reach us. So the skeptic has a fair question. If you cannot see it, how can you possibly claim to know it? The answer is that we are not seeing the first second, we are reading it. The first second did not vanish without a trace. It left physical records, fossils, and we can hold those fossils up against our calculations and check whether the story is true. The most powerful of these records is the helium. We calculated, from the physics of the first minutes, that the universe should have emerged about 1/4 helium by mass, and when astronomers measure the helium in the most pristine, least altered material in the cosmos, that is very nearly what they find. We calculated how much deuterium should have survived, that fragile leftover from the broken bottleneck, and the measured amount matches the prediction with remarkable precision. The light elements are a written record of the first minutes, and the record agrees with the theory line by line. This is not a vague resemblance. The abundance of deuterium, in particular, is so sensitive to the conditions of the early universe that measuring it tells us how much ordinary matter the universe contains, and that number agrees with a completely independent measurement from the afterglow of the Big Bang. Two different windows onto the early universe, the light elements and the relic radiation, give the same answer. That kind of agreement is how we know. There is also the relic radiation itself, the cosmic microwave background, which is the afterglow of the hot early universe captured at 380,000 years. Its very existence is proof that the universe was once hot and dense, because a hot beginning predicts exactly such an afterglow, and a cold one does not. When it was discovered, in the 1960s, it settled a long argument about whether the universe had a hot, dense origin at all, and it settled it firmly in favor of the hot beginning. The radiation has since been measured with exquisite care, and it has the precise character that a hot early universe demands, down to the finest details. The first second lives inside a theory that also predicts this afterglow, and the afterglow is there, exactly as predicted. So the case does not rest on a single fossil. It rests on a web of them, the helium, the deuterium, the afterglow, the faint imprint of the neutrinos, all of them agreeing, all of them pointing back to the same hot, dense, 1-second-old fire. And yet, in the spirit of honesty that this channel tries to keep, we should not pretend the record is perfect, because it is not. There is one crack, one place where the prediction and the observation refuse to line up, and it involves the lithium. The same calculations that get the hydrogen, helium, and deuterium so beautifully right predict that the universe should have made a certain small amount of lithium in those first minutes. But when astronomers measure the lithium in the oldest stars, they find only about a third of what the theory predicts. The universe seems to have less of this element than the first minutes should have produced. This is the lithium problem, and it has resisted explanation for decades. Perhaps the lithium is being quietly destroyed inside those old stars in a way we do not fully understand. Perhaps there is an error lurking in the nuclear reaction rates. Or, perhaps, and this is the possibility that keeps physicists awake, it is a hint of some unknown physics operating in the first minutes, some new ingredient or process we have not yet identified. The lithium problem is a small crack, but it is a real one, and it is a reminder that even our most confident account of the first second has a line we cannot yet read. There is a larger gap too, the largest of all, and it sits at the very foundation of the story. We have spoken of the 1 in a billion excess of matter over antimatter, the imbalance without which the universe would be nothing but light, the reason there is any solid thing at all. We can measure that imbalance, we can trace its consequences, but we cannot explain it. The known laws of physics are very nearly symmetric between matter and antimatter, and a symmetric universe should have annihilated itself completely. Something in the first instance tilted the balance, just barely, in favor of matter, and no one knows what. This is among the greatest unsolved problems in all of science, and it means that the deepest fact about the first second, the fact that anything survived it, is a fact we record without understanding. There is one fossil, that deserves special mention because it does double duty as both a confirmation and a measuring tool, and that fossil is deuterium. Deuterium is exquisitely sensitive to how much ordinary matter the early universe contained. The reason is that deuterium is a stepping stone, quickly consumed as it builds toward helium. So the more crowded with matter the universe was, the more thoroughly the deuterium got used up, and the less of it survived. A universe with more ordinary matter ends up with less leftover deuterium. A universe with less matter leaves more behind. So, if you can measure how much primordial deuterium actually exists, you can read off how much ordinary matter the universe holds with real precision. Astronomers measure that surviving deuterium in ancient, pristine gas clouds seen against the light of distant quasars, and the amount of ordinary matter it implies agrees to within a few percent with the entirely separate measurement made from the afterglow of the Big Bang. Two methods, one from the first few minutes and one from 380,000 years, looking at completely different physics, hand back the same number for how much ordinary matter the cosmos contains. That kind of agreement is not the sort of thing that happens by luck. It is also worth being clear about why the relic radiation settled the question so decisively when it was found. Before its discovery, there were serious scientists who favored a universe with no beginning, a steady state that had always existed and always would, continuously creating a little new matter to fill the gaps as it expanded. That picture made no room for a hot, dense origin, and crucially, it predicted no relic afterglow because there had been no early fire to leave one. The hot beginning picture predicted exactly such an afterglow, cooled by expansion to a few degrees above absolute zero, filling the whole sky. When that faint, even glow was found, coming from every direction at just the right temperature, the steady-state picture could not accommodate it, and the hot beginning could. The discovery did not merely support the hot universe, it ruled out the leading alternative, and the alternatives that linger today, the ideas that try to explain cosmic structure without an early fire, founder on the same rock. They cannot reproduce the precise helium and deuterium abundances, and they cannot account for an afterglow with the exact, smooth, thermal character that a hot beginning demands and that careful measurement has confirmed. So here is the honest shape of our knowledge. We can predict the helium of a galaxy we have never visited from the physics of a second we can never see, and we are right, again and again, across the whole sky. And in the same breath, one line of that ancient record, the lithium, comes out threefold wrong, and the most important fact of all, that there was any matter to begin with, we cannot account for. We are reading a document written in the first second of time, fluent in most of it, moved by how much of it we can understand, and still unable to translate the single sentence that says why we are here to read it at all. That mixture of mastery and humility is perhaps the truest picture of where we stand. We know the first second astonishingly well, and we do not know it completely, and both of those things are worth sitting with. There is one more thing to say about that second, though, the most personal thing of all, and it has to do with the long shadow it casts, all the way down to you. Part 12. The fire that cooled into us. Everything that exists was in that fire. We have circled this idea a few times tonight, but at the end, it deserves to be said plainly and slowly, because it is the truest thing about the first second. The matter that makes up your body, the matter in the chair beneath you, in the ground under the building, in the moon and the sun, and the farthest galaxy you have ever seen a picture of, was all present in the universe at 1 second old. It was not somewhere else. It was right there, in that smooth, blinding, billion-degree fire, pressed together, churning, too hot to be anything yet. The first second is not a stranger to you. It is your oldest ancestor, the common origin of every particle you are made of, and the fire that cooled into us has never really been anywhere but here, growing slowly quieter across nearly 14 billion years. Trace your own substance backward, and the path leads straight into that second. The hydrogen in the water you drank today was forged in the first minutes, its bare protons among the survivors of the Great Imbalance, its proportion to helium set when the coin froze in the air. The deuterium dissolved in every ocean is a survivor of the broken bottleneck, a fragile nucleus that formed in the first minutes and was never made again. The carbon and oxygen and iron in your body came later, from stars, but the stars themselves were born from the hydrogen and helium of the first minutes, lit from the recipe that the first second wrote. Pull on any thread of yourself, and it runs back through the stars, through the cooling gas, through the forging of the light elements, to that 1 second when the universe set the proportions of everything. You are not separate from the early universe. You are what a small part of it became, after a very long time spent cooling and gathering and growing complicated enough to wonder where it came from. And the relics are still with you, which is the part that refuses to feel abstract. The cosmic neutrino background, released at the instant the ghosts went free, is passing through your body as you listen. Hundreds of those ancient particles in every cubic centimetre of you, a fossil older than the oldest light, streaming through your skin and your bones and onward into the dark, exactly as it has streamed through everything since the universe was 1 second old. The relic light of the early fire fills the sky in every direction, the faint cold afterglow that telescopes read like a page. You are not looking at the early universe from the outside, across an unbridgeable gap. You are inside its aftermath, made of its leftovers, washed continuously by its fossils. The first second did not end and leave you behind. It is still here, in the most literal way, in the cold neutrinos moving through you and the ancient light filling your sky. There is a phrase we started with, almost clinical when we first said it. The universe was 1 second old. We meant it as a measurement then, a setting on the cosmic clock, 10 billion degrees, 1,000 suns in every direction. But hold the phrase now, at the end, with everything we have learned behind it, and it changes. The universe was 1 second old, and in that single second, shorter than the breath you are taking, it freed the oldest fossils in existence. It locked in the proportion of its 2 basic building blocks. It stood at the threshold of forging the first elements, and it decided, in ways it could not undo, what you and everything around you would eventually be made of. 1 second old, and already the recipe of your body was being written. 1 second old, and already the books had failed to balance in exactly the way that allowed you to exist. The phrase is not clinical at all. It is almost tender. The universe was 1 second old, and it was already deciding us. The same fire that freed the oldest fossils and froze the cosmic recipe was, in the same breath, setting in motion everything that would one day gather into a world with someone on it asking these questions. There is no clean line between that fire and you. There is only a long, unbroken cooling, 14 billion years of it, leading from the smooth, blinding plasma to the quiet evening in which you are listening to this. The first second was not the universe's business and yours a separate matter. It was the opening of the only story you have ever been part of. There is a particular kind of vertigo in following that thread all the way down, and it is worth letting yourself feel it rather than rushing past. We are accustomed to thinking of our origins in human terms, our parents, our ancestors, the long line of living things stretching back across the ages. But the line does not stop at the first living thing. It runs on through the dust that formed the earth, through the cloud that collapsed into the sun, through the stars that forged the carbon and oxygen, and back through the cooling gas to the first minutes, where the hydrogen and helium themselves were made, and from there to the 1 second when the proportions were set and the fossils were freed. You have an ancestry that predates biology entirely, a lineage written not in cells but in nuclei, reaching back to a fire that filled all of space. The first second is not a chapter in someone else's story. It is the first line of yours. And there is a gentleness in realizing that the universe did not have to leave us any way of knowing this. It could have erased its own beginning, leaving no fossils, no relic light, no surviving deuterium, no count of helium, nothing for a later mind to read. Instead, it kept the receipts. It left the afterglow filling the sky, the neutrinos drifting through every body, the light elements salted through every cloud of gas, a physical record of its first second preserved across 14 billion years, until something came along curious enough and patient enough to decode it. That something is us. The fire cooled and gathered and grew complicated, and after a very long time, it produced beings who could look at the helium in a distant star and the cold glow between the galaxies and reconstruct the second of their own birth. The universe wrote down its beginning, and then, eventually, it grew an eye to read it. What lingers, when the numbers settle, is how much was determined so early and so fast. We like to imagine that the important things take time, that significance accumulates slowly, that the deciding moments are spread across the long ages. And much of the universe's story is slow, the patient gathering of galaxies, the long lives of stars, the unhurried drift toward complexity and life. But the foundation, the recipe, the proportions of matter, and the freeing of the fossils was laid in the very first second, before the universe was old enough to be measured in minutes. The cosmos did its most decisive work in its first heartbeat, and then spent nearly 14 billion years living out the consequences. We are among those consequences, late arrivals to a story whose opening line was written before there were stars to read by. And the opening line is not fully translated yet. We can read most of that first second with a confidence that still amazes the people who study it, and there remain, woven into it, the sentences we cannot yet make out, the missing lithium, and, beneath everything, the unexplained reason that any matter survived at all. The universe was 1 second old, and it left us a record we are still learning to read, a record that is, in the end, a record of ourselves, of where our substance came from, and why there is something here rather than nothing. The fire cooled into us, and we turned out to be the part of it that looks back and asks how it all began. There are more questions waiting in that first second than we have answered tonight, and some of them may be the ones that finally tell us why the universe chose to make anything at all.